I forgot my charger today, so we'll see if we can get through this. If not, we'll go old school. Alrighty, so questions. PA2, ODPs, stacks, other things. ODP makes sense? Cool. Okay. Mm-hmm.
The output is 1, 2, 3, 0.
Mm-hmm.
And 1, 3, 0. Or 1, 0.
That's the null terminator on the last node. Because I wanted to make sure you didn't change it. The main program you're assessing is kind of arbitrary to you, right? It's okay to look at it and experiment with it, but I usually make it deliberately a little convoluted. Not that I expect people to do dishonest things here, but for example, if you're trying to write a program that sorts a set of numbers, I might write a test bed that lets me specify a set of numbers on the command line and then sorts them using your sort function and prints them out, right? Well, if you didn't feel like writing a sort program and you knew what my main program was doing, then you could simply write a program that, you know, calls the sort function or something from Unix, or something that just prints out the answer, right, the sorted numbers. So I kind of deliberately try to make it not totally obvious what the main program is doing. So if you run the main program that you've linked into with the test bed and you run it, it might just segfault, right, because it's expecting arguments, or you might put in a number and it gives you some really weird number back, right? That's why I say you can't use that test bed program to debug your function. You got to use your own program because it's going to be confusing what it's actually doing. It just depends how I set up the ODP, and I'm experimenting with different ways to set these up, and it's a evolutionary process. So, but yeah, in that case, it was just the null terminator. Other questions? All right, let's talk about implementing stacks. So a very natural way to implement a stack is with an array. So we'll deal with integers today, but again, a stack could be anything. It could be a stack of strings, it could be a stack of lists or hashes or anything else. We'll just deal with stacks of integers. It's the most common use case in an OS, at least. So let's just make an array of integers, and let me call it stack. And I'm making a small stack. It's only going to have 10 integers in it. So what's the last index in my array? 9, good. Stack bracket 10 does not exist. Possible segfault if I try to hit it. So the convention I'm going to use for the first round here is that when you push something onto the stack, I'm going to store it right here in index 0. And the next thing you push, I'm going to store in index 1, and the next thing in index 2. So I need some way of knowing where I'm going to store the next thing that I push. So we have what's called a stack pointer. It literally points to the stack, right? So with this convention, I'm going to initialize it to 0. And so SP is telling me where the next push will be stored. So SP always says, where am I going to store the next thing that I push? So if I want to push the number 5, I'm going to store it at the index given by SP, that's index 0. And I need to increment the stack pointer so that the next time I push, I'll store at index 1. So my stack pointer started off at 0. I just pushed, now I'm going to increment it to 1. And if I say push a 7, stack pointer says store it at index 1, and I'm going to increment my stack pointer to 2. And so we can write a general algorithm for push. Push some number n says take the element at the stack pointer, set that equal to n, and then increment the stack pointer. And we want to increment after we've used the stack pointer to store this n. So we could also do that by doing SP++. So a post increment. Everybody's comfortable with the plus plus minus minus thing, right? If it comes after, it says use this variable, and when you're done, increment it. If it's before, you increment first. So our push is really just a single operation. Stack SP++ equals n. All right, what should a pop do? Right now, our stack pointer is 2. If we say pop, we want to return the 7. That's the last thing we pushed. But it's not at location 2. It's at location 1. Right? Because after we pushed the 7, we incremented the stack pointer. So if we want to retrieve the last thing we pushed, we should do decrement the stack pointer and then return the element at that index. So when we say a pop, we'll decrement the stack pointer to 1 and we'll return the 7. Yes?
So what would happen if you just said return stack SP minus minus? Would it still decrement SP, or would the return how would that go?
If we do SP minus minus, the stack pointer will get decremented, but if our stack was, let's go back to where it was 2, it would actually return the element at index 2. So yeah, we need minus minus SP, as you said. So pre-decrement, post-increment. So that's exactly how we can do a stack pop. So decrement the stack pointer and return the 7. And if we say pop again, this will say decrement the stack pointer and return, in this case, 5. So push and pop are basically single operations. But push is a post-increment, pop is a pre-decrement. So let's note that. So post-inc, pre-dec. So how do we know when the stack is full? Let's start pushing things. We push something here, SP will become 1. Push something here, SP will become 2. SP is always the next location we're going to push. So after we've pushed something into location 8, the stack pointer will be 9. After we push something here, the stack pointer gets incremented to a 10, and our stack is full. So our isFull function SP equals 1 plus the index of last element, which is also the number of things in the array, right? If we initialized our stack to be an array of 10 integers, then when SP equals 10, we know the stack is full.
If you do one equal sign like that, isn't that just going to set it?
Yeah,
If you-
it's pseudocode.
Oh,
Because you can't say index of last element either, but good for catching that. So if the stack pointer is equal to the index of the last element, or if it's equal to the number of elements in the array, right, then the stack is full. So how do we know if the stack is empty? Someone said it. Yeah, if your stack pointer is equal to 0. Pretty straightforward. So a little sidebar here. We pushed on a 5, we pushed on a 7, we did a pop which pulled off the 7, we did a pop which pulled off the 5. If I were to manually go in and look at this element in my stack array, what do I find there? I find this value that I pushed. Even though I've popped it off the stack, it didn't disappear, right? There's nothing in memory that suddenly just poof, vanishes, leaving a hole or something, right? Everything's got some collection of bits associated with it, every memory location. And unless you do something more than this, when you pop something off a stack, it's still sitting in that stack memory. If this was somebody's password that was stored in a local variable, which means it's on the stack, and you exit the routine, it's still sitting in memory, right? Potential vulnerability. So popping is not the same as, expunging from the record. Stuff still sits in there, and there have been exploits that take advantage of that. All right, well, this is one version of a stack, but there's other versions we can make. For example, we could say stack pointer equals location of the next pop. Instead of telling us where we should push the next thing, we could say stack pointer is going to tell us where we should pop the next thing from. And so in this case, our initialization would set SP to -1. And our push, well, our pop will just return the element at the stack pointer, but we want to decrement it after we use it. But now if we have our stack array, so SP equals -1, and we want to push a 5, we can't just use stack pointer to tell us where to store that 5. We have to increment it first and then store the 5 at that location. So increment this to a 0 and then store at index 0. So this is a pre-increment. Now if you want to push a 7, increment the stack pointer to a 1, store the 7 at that index. If you want to pop, read the element from the stack pointer and then decrement, so post-decrement. It's another way to implement a stack, pre-increment for push, post-decrement for pop. Perfectly valid. But the behavior of your elements in the array is a little different. And to initialize, we have to start off with the SP equals 0. And under this realm, an empty stack is indicated by the stack pointer being -1. What would a full stack be? Almost. -1, yeah. So if it's full, it's index of the last element. In our case, 9. Because if the stack pointer is equal to 9, it means we've pushed something into this location. That's where we're going to pop next. If we try to push again, it's going to increment the stack pointer to 10 and then store something at element 10 that's out of bounds. So our full and empty conditions change slightly. The initialization changes slightly. And the push and pop change slightly. Well, here's another way that I can use a stack. If I want to push a 5, I can store it in this last element of my stack and then decrement the stack pointer. So when I push a 7, I use the stack pointer, store it at that location, decrement the stack pointer again. So a push looks like this. It's a post decrement, and a pop is a pre-increment. So if I want to pop, let's see, if I want to pop, I'm going to increment my stack pointer to an 8, and I'm going to return element 8. That gives me a 7. If I pop again, I'll increment my stack pointer to 9. I'll return element 9, which gives me my 5. And here, our stack is empty when our stack pointer equals 9. And it's full after we push into location 0. So we push into 0 and we decrement. So your stack pointer is equal to -1. And there's a fourth version we can do this, which would be growing from the higher indices to the lower indices, but push would become a pre-increment, pre-decrement, and pop would become a post-increment. So there's at least 4 different ways to implement stacks using an array. Which one is better makes no difference in some sense, but it's important enough that on a lot of ARM processors, there's configuration bits you can use to actually dictate which way the stacks work. Pre or post increment or decrement for push. So flexibility. Now on a lot of computers, a lot of operating systems, stacks are set up to grow from higher addresses to lower addresses. So let's just think of a 32-bit machine. So the last location would be 8 Fs, right? 2 billion something. And up here is location 0. And usually, you know, some stuff up here is like operating system and user code and other things like that. And then there's a big gap, and then this lower area is stack space. And your stack grows in this direction. And one advantage of doing that is that you always start your stack at this address, no matter how big it is. Now, if you have a system with a little bit of memory, your stack space might only go up to here, and that's it. You might have used up all the memory. So your condition for being full will be when you go beyond that bounds, but you still start with a stack pointer pointing to this fixed location. You put in more memory into your machine, and now your stack goes up to here, and you still start at the same location. Your stack still grows. It just takes longer for it to get to this region where it's going to get an access error. So growing the stack to smaller addresses has this advantage of not binding you to a particular size of stack. And if you've got lots of memory, a lot of it's usually used for stack space. So let's run through something that we did yesterday. See how my battery's doing. We got 11 minutes of battery left. We ain't gonna make it. All right, I'm gonna stop recording.